Good evening. Just so you know, this is when I get to work, when I'm not being a grade triple R and a grade R teacher. Shannon told me the other day, now that I'm teaching them, I can pretend like I'm a real teacher. So here is your next lesson from a real teacher. So remember at the end of the previous one, we said we're going to start by marking the homework. So get out your answers to exercise 3 and let's go through it. It says the following compounds are given: BF3, CO2, SO2, H2S, CCl4, and H2. Choose compounds from the above list to answer the following question. Which compound is nonpolar and has nonpolar bonds? That would be hydrogen. Which compound is a nonpolar molecule, but it contains polar bonds? You could use either carbon dioxide or carbon tetrachloride there, because the difference in electronegativity makes the bonds polar, but both ends of the symmetrical compound are negative. So there's no pole between one side and the other side, positive and negative. So it would be non-polar as a molecule. 1.3, which compound is angular and contains double bonds? It would be SO2. Which compound has one atom which has two lone pairs of electrons? H2S. Which compound is trigonal planar? That would be BF3. Number 2, what does electronegativity measure? It measures the tendency of an atom in a molecule to attract a bonding pair of electrons. Use the periodic table to answer the following questions about the first 20 elements. Just note here it says 20 elements because I wanted to make that mistake and use the whole periodic table. Where is the most electronegative element found? It's group 7, period 2, which is fluorine. And where would you find the least or the lowest electronegative compound? Group 1, period 3, potassium. And you could also have said group 8 because your noble gases obviously don't have an electronegativity. And yeah, the reason it's potassium and not francium and cesium here is because you are only looking at the first 20 elements. Which atom would tend to form a positive ion? Use their electronegativity. Sodium or bromine, it would be sodium. K or Cl, K. H or O, H. Mg or S, it's Mg. Now I made a little note here in my book. Each time it is the one with the lower electronegativity. Yes, we also know it's the positive one because we know it's the left-hand side. It's the metal of the left-hand side of the periodic table. But each time as well, if you look at them, it's the one with the lower electronegativity. Then the last question says, give the difference in electronegativity for the following bonds and say whether they are ionic, non-polar, or polar. 5.1, oxygen, O2. Its difference in electronegativity would be 3.5 minus 3.5, which is equal to 0. So it's a non-polar covalent bond, but even more importantly, it's a pure covalent bond, like all the diatomic molecules. The second one, MgO, the difference in electronegativity is 3.5 minus 1.2, which is 2.3. That would make it an ionic bond. The third one, the difference in electronegativity is 3.5 minus 0.9, which is 2.6, which also makes it an ionic bond. And the last one, 3.0 minus 2.1 is 0.9, which is a polar covalent bond. Then if we look at the test question that I gave you, first question, the definition of electronegativity. It is the measure of the tendency of an atom in a molecule to attract the bonding electrons. 2.2, that is OF2, but more technically correct would be if you'd drawn it bent and both lone pairs at the top, but it's not a known molecule, so I accept it either way. The difference in electronegativity is 4 minus 3.5, which is 0.5. Therefore, the bond is slightly polar, it's weak polar. 2.4, and please note how this is answered. The bonds in both molecules are polar. This is due to the difference in electronegativity. The shape of OF2 is bent, meaning the charge distribution around the central atom is asymmetric, therefore the molecule is polar. The shape of the CO2 molecule is linear, and because the charge distribution is symmetrical, the molecule is non-polar. Right, so that brings us to the end of exercise 3 and the section there on, what was it on? Oh, electronegativity. So now let us have a look at this new section where we're going to be speaking about bond energy and bond length. So what you need is you're going to need to make sure you have PowerPoint 4, or it's called M&M 4, downloaded from the school's website. You need the textbook where we'll be working from page 34 to 40. That includes exercise 4, which is going to be homework. And once again, you need your definition booklet. So if we look at the simple and the straightforward definition of bond energy, or bond enthalpy if you want to use the fancy word, the simple definition is that it is the energy required to break a bond. However, if it is asked for you in a test question, you need to state it as following. It is the energy needed to break 1 mole of its molecules into separate atoms. Also, the amount of energy released when a bond is formed. You need to mention that bit about it being 1 mole of molecules when you define bond energy. Bond length, quite simply, is the average distance between the nuclei of the 2 bonded atoms. And bond order refers, or it's an indication of the amount of bonds between atoms. It refers to the number of bonds between 2 atoms. So a single bond would be bond order 1. A double bond would be bond order 2, and a triple bond would be bond order 3. So now let's put all of this information together. A double bond would require more energy to break than a single bond. And a triple bond would require more energy to break than a double bond. Thus, as the bond order increases, so does the energy required to break the bond. Also, the bond length decreases as the bond order increases. So a double bond is shorter than a single bond, but a triple bond is shorter than a double bond. So if we look at the following example, there's carbon single bonded to a carbon, carbon double bonded to a carbon, and carbon triple bonded to a carbon. The length of a single bond would be 154 picometers. Remember, pico is times 10 to the minus 12, so it would be 154 times 10 to the minus 12 meters. A double bond is shorter at 135 picometers, and a triple bond is even shorter at 120 picometers. It is far easier to break the single bond, as you only require 348 kilojoules per mole to break them. It is a bit harder to break the double bond, requiring 619 kilojoules per mole. And it is hardest of all to break the triple bond, requiring 839 kilojoules per mole. So bond energy is influenced by both bond order and bond length. So if we look at the following example, if you are required to calculate the bond energy to break up 1 mole of molecules of methane, the first step that you would need to do is to draw the Lewis structure. Next, you'd have to look up in the table what is the bond energy to break a CH bond. Now note, you will never ever have to learn any of these numbers. They will be given to you, or you will be able to read them off a table or a graph. So if you look in the table on your textbook, the bond energy to break up a CH bond is 413 kilojoules per mole. Now, in a mole of methane, or in a molecule of methane, there are 4 CH bonds to break. So 4 times 413 is going to give you 1,652 kilojoules per mole. So in other words, the amount of energy I would need to break up 1 mole of methane molecule is 1,652 kilojoules. So remember, you're always going to be given this information. Now, we also need to be able to look at this on a graph. There are various forces of attraction and repulsion between atoms in a molecule. So in order for a bond to be formed, electrons must be attracted enough by the other atom's protons, resulting in potential energy being able to be stored. When bonds break or forms, it is the potential energy that changes. Now, if we look at the graph of the change in potential energy of two atoms who are wishing to form a bond, let's start on the right-hand side. There are two H's far apart in space. They are trying to find each other. They're a bit like starstruck lovers. Because they are so far apart, there is at this stage no attraction between them. Hence, a very close to zero potential energy. As they move closer going left, which means their bond length is decreasing, they gain potential energy till the point where they are optimally separated. And this is where the perfect nonpolar covalent bond forms. It is the optimal bond length, which as shown in this diagram is 74 picometers between the two hydrogens. However, if they get too close, like if they are stuck in lockdown together for 21 days, they start smothering each other. And the protons in the nucleus repel and they get ugly, uncomfortable energy. And that is where it rises on the left-hand side. So please make sure, and if you look there where they're too close, neither of the hydrogens are happy. They're too close, it's overdone, it's there. Optimally, they have a low potential energy, everything's nice. Too far apart, there's no bond between them, so there's no energy. Please make sure you can read this graph. And remember now, the x-axis is bond length. So you're looking at how far apart the bond is. I know there's the temptation to always want to look at an x-axis as time. This is not time, it is length. So on the very left-hand side, it is a small bond length where it's too close together, so it's a non-optimal bond. At exactly 74 picometers is the ideal bond length. And as we move right, it's too far apart. The y-axis is representing the bond potential energy. So please do this example. It is from question 2 of last year's June exam. It's the bottom part of it. So let's pause the video quickly now, complete the question, and then check your answers. 2.5.1, X is representing the bond energy, Y is representing the bond length. 2.5.2, it's the energy needed to break 1 mole of its molecules into separate atoms. And 2.5.3, the higher the bond order, number of bonds between atoms, the shorter the bond length, the stronger the bond, and thus the bond energy increases. Right, I hope you got those right. They're not too difficult. So next, I'd like you now to do exercise 4. But I just need you to do number 2, number 3, and number 6. Again, I'd like you to pause the video, do the exercise, then get the answers. Right, I trust you paused the video and you're now back. Here's the answers. Number 2, 2.1 is 946 kilojoules per mole. 2.2, 926 kilojoules per mole. 2.3, 431 kilojoules per mole. 2.4, 243 kilojoules per mole. 2.5, 676 kilojoules per mole. And 2.6, 2271 kilojoules per mole. Question 3, atomic size, bond length, bond order. And question 6, 6.1.1, bond length. 6.1.2, bond energy. 6.2.1, bond length. The independent variable is on the x-axis. 6.2.2, it's a hyperbola. 6.2.3, he must not use all the values. He must only use the data in which the controlled variable is constant. 6.2.4, only use the carbon bonds that are single bonds, namely CC, CO, and CH. This now brings us to the end of Unit 1 of Matter and Material on atomic combinations. All of this that we've done, including the stuff we did still at school at the end of Term 1, will make up question 2 at your end of your paper, probably about 15 odd marks. Please complete the end of section questions on page 47 to page 50 of your textbook. Please do all of them and make sure you completely understand this section before going on. I'd like you to finish this section by Wednesday, so on Thursday we can start the next section of work. I trust you having a good time, and I hope you understand this. If there are any questions, remember either WhatsApp me, call me, leave a comment, and I'm sure we will chat soon. Goodbye.